again, changing or a decay of the atomic nucleus through giving off some sort of particles. And again, those particles are alpha, beta, or gamma particles. Alpha particle physically changes the nucleus. Beta particle physically changes the nucleus. Gamma particle doesn't necessarily physically change the values, but it changes the structure of the nucleus. But that's a little bit different. So then over here to number 11, transmutation. So I said for in one element turns into another. I'm going to kind of add to this as like a physical changing of the nucleus. So for example, we talked about alpha decay. So we said alpha decay gives off a helium nuclei. So the atomic number decreases by 2 and the mass number decreases by 4. So we go from something like uranium-234 to thallium-230. And that is what I'm talking about. That's a physical change in the nucleus. Like the nucleus actually is something very different now than it was. It's a completely different element. Likewise down here when we talk about beta decay, so by giving up an electron, I change a neutron into a proton. And when I do that, I change the atom. The atom now is 1 proton higher than it was, so it's a completely different element. So it's not just changing, it's not just like, oh, it's still uranium. Like, it's completely different. It's not uranium anymore. It's something else completely different. The example I gave here, well, let me give you an example here on this one. So a good example of beta decay transmutation would be, hold on, let me get my chart that I want here. So going from lead-210 to bismuth-210. So if I go from lead-210 up to bismuth-210. What? Oh, yeah. Okay. So that's kind of the idea of what's going on there. Okay, so just kind of to clarify transmutation a little bit more and how that's different than radioactivity. So radioactivity is any sort of kind of give off a particle, but transmutation is specifically when the nucleus changes into something else. So gamma decay is not transmutation because it stays the way it is. Okay, it stays the way it is. It just gives off these higher energy things. All right. Artificial transmutation and how it's different than natural. So artificial is forced, so I make it do that. Natural transmutation occurs on its own. So let me show you an example of this. All right, here we go. This is the transmutation of uranium-238 into lead-206. Okay, so you start with uranium-238. It does alpha decay down to thallium. It does beta decay up to palladium, back up to uranium-234 this time. Then it goes down to thallium again, this time thallium-230, then down to radium-226, and so on and so forth. Okay? So it's the physical process of changing from something that is radioactive, U-238, to something that is stable, lead. Okay? So that's what I'm talking about when I'm talking about transmutation. This can be natural, like this itself happens naturally over time, or it can be forced. I can make it decay and destabilize it. Okay? All right, we'll come back to that. The last one here, though, explain radioactive dating and how it can be used to determine the age of a material. Okay. So, you've probably heard of carbon dating before. They use it to figure out like how old Like, you find somebody's bones, and you're like, how old is this dead person? And you, like, do carbon dating to figure out how old they are. Radioactive dating isn't just for carbon. It's sort of anything. So the first thing you do is you look at something that you want to figure out. And the example we're going to use is a rock. So I got a rock that I found. And I look at the rock, and the rock is mostly uranium. So let's do like a pie chart. Let's say about half of it. About half of it is uranium-238. So about half this rock is uranium-238. And it's not like this. It's not like the left half is uranium and the right half is... It's like just spread out throughout the whole thing. But about half of the stuff in the rock is uranium-238. The rest of the stuff that's in the rock, you find stuff like some of it is thallium-230. You got some lead-206. Like there's other stuff in it. So it's not just uranium-238. There's other stuff in it. So you got this rock and you look at it and you're like, it's got things. Sweet. Okay. The first thing you do is you figure out what it's the most of. So it's mostly uranium-238. And we know the half-life of uranium-238. So the half-life of uranium-238 is, anyone know that off the top of their head? Anyone got that one? No? Don't have the uranium-238 half-life memorized? It's all right. 6? It's a good guess. It's 4.5 billion years. 4.5 billion years. 6 is close. You're almost there. Yeah. Okay. So we know the half-life uranium-235 is 4.5 billion years. And if you're wondering, how do we know that? Because we haven't lived, us humans, 4.5 billion years. So now how do we know that half of the uranium is left after 4.5 billion years? You can take a small sample of like pure uranium-238 and you can like force it to undergo transmutation and you can figure out like the rate at which that occurs over a shorter period of time. So without having it to be billions of years, you can figure out what it is over a shorter period of time. So we've done that with all types of radioactive materials. And so for uranium, we figured out that the half-life of uranium-238 is 4.5 billion years. That means, again, if we go up here to half-life, where did I do half-life? Here. So it's the time it takes for half of the material to decay. So that means that after 4.5 billion years, half of the material should have decayed. Okay, half of the uranium-238 should be decayed. Okay, so we know the half-life of uranium-238 is 4.5 billion years. So, how much of the rock is still U-238? How much of the rock is still uranium-238? So I look at my rock and I say half my rock is uranium-238. So how old should the rock be? The rock should be 4.5 billion years old. Because that's how long it takes half of uranium to decay. And half-life is a very, very, very consistent value. If you're wondering, you're like, well, how do I know exactly half is going to decay after that long? It's kind of like, remember we talked about temperature? We said that temperature is an average. Okay, so if it's 78 degrees, that means the average of all the temperatures is 78. So some of the particles are a little faster, some of the particles are a little slower, but in general, they have the energy of 78 degrees. That's what half-life is like. So some of the uranium-238 decays quickly, and some of the uranium-238 decays over a long period of time. Just depends on the individual nucleus of uranium and how stable it is. Whether something else hits it and destabilizes it, or whether whatever happens in order to cause it to be stabilized. And so another question I get is, okay, so let's say that half the uranium is 238. How do I know that that rock, that's just not how the rock was, right? Like, how do I know that this just wasn't a rock that had half of the rock be uranium-238? Like, how do I know it was pure uranium-238 to start with? Well, the way I can tell is if I look at the rest of the rock. What else is the rock made of? So the rest of the stuff, the non-uranium-238 things. If I look at the rest of that, the rest of the rock is going to look like this. The rest of the rock I'm going to find is this stuff. And based off of what these things are, I can figure out what their half-lives are. And so I can figure out like how much should be uranium-238 and how much should be thallium-230 and how much should be lead-206. So I can figure out how much of that stuff is there actually in it and how much of that stuff should there be. And based off of that, I can figure out how much stuff is there. And is it actually, should it have been pure uranium-238 at some point in time? If you've ever wondered, why do we think the solar system is 4.6 billion years old? This is why. This is why we think it's 4.6 billion years old. Because we did uranium dating on a bunch of uranium rocks all over the planet, and we find that these rocks are all about the same consistency of materials inside of them, and half-life of uranium is fairly consistent, and that's where we figured it out from. So it wasn't like some dude was like looking at rock layers and was like, oh, there's 4.6 billion. It's not like a tree or something like that. Like they were looking at these materials, and you can go back in time. Like if you've ever wondered, like how did they know how long ago the ice age was and that kind of stuff. You can do the same thing with different materials. And so depending on what the material is, it might not be 4.5 billion years old. The rock may be 25%, or sorry, it may be 75% uranium. That means that rock is not 4.6 billion years old, 4.5 billion years old. It means it's 2.2 billion years old. So you can figure out how old something is by looking at what the thing is. If it's pure uranium, then it's not very old at all. And so you can figure out that stuff. So that's where that came from. If you've ever wondered, how do we think the universe, or not the universe, that we'll get to later. How do we think the solar system is that old? That's how we figured it out. We look at, and we've done it not just for Earth. We've done it for asteroids. We've done it for Mars. We've done it for lots of different things. And they all come up about the same age. They all come out to be about the same age, based off of the materials that we see. Okay, so very helpful, very useful in figuring out the dates of things, and kind of interesting to think about how all that works. So any questions on notes 2? Any questions about radioactivity or any of that kind of stuff? Sweet. All right, let's take a short brain break, and then we're going to jump into the notes for notes 3. But let's first, well, let's stop recording. Let's